In today's video, I would like to introduce a very nice problem involving the convergence series. So this type of the series is written on the form of the inverse of n to the s. Okay. So as we saw before, previously we saw the harmonic series, which was written on the form of the sum as n goes from 1 to the n, 1 over n to the s. S as an exponent, when I have s it was 1. But this time I have changed the exponent to number 2. Generally, this series is written on this form. As n goes from 1 to infinity, for example, 1 over n to the s. Okay? S equals 1 as an exponent is called the harmonic series. Okay? Now this time we are going to see when we have s is strictly superior than 1. A harmonic series is a particular case when we have s equals 1. Okay? It was a diverge series. We already proven this one in the previous video. Now let's go through our example. We know for all n is superior or equal to 2. We know n squared is strictly superior than n squared minus n. Okay, it's very clear. Now I'm going to take the reciprocal of this one. So I will have 1 over n squared is strictly inferior than 1 over n squared minus n. So when we take the reciprocal of this one, this inequality is changed the direction. Okay. The next thing, I'm going to apply the sum notation on both sides. So we'll have the sum of 1 over n squared as n goes from 2 to infinity, because we already have chosen n is superior equal to 2, which is strictly inferior than the sum of 1 over n squared minus n as n goes from 2 to infinity. Okay. We cannot apply n equals 1 because the denominator becomes 0. Okay, that's the reason why I'm choosing n is superior equal to 2. Okay, so now I'm going to evaluate this one. So I have the sum of 1 over n squared minus n as n goes from 2 to infinity. I'm going to transfer this one into decomposition form. So I have 1 over n squared minus n equals 1 over n factor n minus 1. I'm just taking n as a common factor for the denominator, so I get this expression. I'm going to use the trick to split this one into two terms. So this one is the same as 1 over n minus 1 over n. So now if I'm trying to distribute, this one is giving us factoring out the denominator, I will get this one. So I'm going to work out on the numerator. I will get n minus n plus 1. So n will be cancelled out. I will be left with 1 in numerator. So 1 over this one. So it's taking me to the previous expression. Okay. I'm going to apply the sum notation on both sides. So we'll have here, this one is the same as 1 over n minus 1 over n under one sum from n, it goes from 2 to infinity. Okay, so I'm going to clean up this one. We don't need this one now. So now I'm going to work on this one. So I'm going to expand this one and apply the limit on this one. So as I have here, this one 1 over n minus 1 over n. So this one is the same as the limit as capital N goes to infinity of the sum as n goes from 2 to capital N of 1 over n minus 1 over n, like this. Okay, so I'm going to expand this one. So I will have, let's call this one as a capital A. Expanding this one out, I will get 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, like this, and so on and so forth until you get the last term, which is 1 over capital N minus 1 over capital N, like this. Okay, now I will have a lot of cancellation here. This half will be cancelled out with this half, this third will be cancelled out with this third, this quarter will be cancelled out with the 1 after this one. So this capital N minus 1 will be cancelled out with right before this one. I will be left with capital A equals the limit equals 1 minus 1 over capital N. This inverse of this one is going towards 0. So I will have 1 minus 0, which is 1. So I have calculated the limit of this one, which means this one is given as a 1. Okay. Since this series is strictly inferior than this term, so we found this one is as a convergence series because it equals 1. Okay. Which means this one is a convergence series. This one is arithmetically is a convergence series because this series is a smaller than this series. Okay. But be careful here. We have determined just this sum. We don't have any. It goes from 2 to infinity. But it's been asked to prove as n goes from 1 to infinity. So it's very simple here. This one, as n goes from 1 to infinity, of 1 over n squared. I'm going to split this one into two terms. I will have number 1 here plus, and it goes from 2 to plus infinity of 1 over n squared. So we already determined this one, it was a convergence series, which means this one is arithmetically a convergence series. Okay. Now the most important observation that I have observed here, we have these sums. If S is superior or equal to 2, like this, as a capital A, let's mean a capital A as a series is a convergence series. But if S is strictly inferior than 2, capital A becomes diverge series because it's a harmonic series. We have proven this one in the previous video. So I have done with this proof. Now for the next video, I'm going to calculate this sum as a convergence series. Okay. If you are interested in this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you next video. Bye.